Hello, everyone, and welcome to the newest episode of Oh My Lloyd, Math with Miss Lloyd. It's been a while because I've been on summer vacation and I'm not going to work when I'm not being paid. So, this is a prerequisite that I'm doing with my students. I am trying um, a flipped classroom this year. And so I'm going to be sending my students these videos on the notes, and then we're going to do a few examples in class. So not every example that is on my little list here is going to be done on this video. I'm going to save some of them for my students because they're my bebés and I love them and I want to make sure that they get some face-to-face time with me and with these examples. So hopefully you guys can bear with me. If any of this is familiar, just fast forward. It's fine. This is, again, a prereq, and so we're kind of just going over things that you guys could kind of hopefully already know or have an idea of. So the first thing I want to look at is real numbers. So there are a lot of different types of real numbers. Real numbers go from negative infinity to positive infinity, and all these places in between. The different types, and we know something is a real number because it's not imaginary, so it doesn't have an I with it. We haven't tried to take the square root of a negative number. Within the real number system, you have either rational or irrational numbers. They're two different, so I don't have them in the same space. They're next to each other because they are both real. Rational numbers can be represented by an integer over some kind of natural number, so something over 2, over 3, over 4, etc. It can be a fraction. When it comes to irrational numbers, they can't be represented with fractions. So you have things like pi, which is 3.14159, and then it just kind of keeps going, and people are really impressed if you know a lot of those digits. We also have things like the square root of 2. The square root of 2, that decimal just goes on forever, and it doesn't actually make sense. So like people could say that 1/3 goes on forever in decimal form because it's 0.3 repeating, so the threes just keep going. But we know what's going to happen next. It's not impressive if you know 1/3 the decimal point to the thousandth place because you just say 3 a crap ton of times, well, 1,000 times. And so it's not as impressive. Irrational numbers, they go on forever and they don't repeat. So no part of it at all is repeating. Within the rational number system, we have integers and non-integers. So non-integers means we have fractions, we have decimals. It's not what people would typically say as a whole number, and whole number is a little bit different. So when it comes to integers, so not a fraction, not a decimal, we have either whole numbers or negative integers. So whole numbers aren't negative. You can't have a whole -3 papayas. I don't know why I said papaya, but that's the first thing that came to my mind. So negative numbers didn't really exist for a while. They started because they represent being in debt. Like someone needed a representation of being in debt, and so they created negative numbers. Within whole numbers, so whole numbers start at 0, and they're basically all of our counting numbers. But 0 is not considered a natural number. So if you look back, there isn't a year 0. 0 wasn't invented until around 300 AD. So until after what would have been year 0, you're not counting anything. You're not talking about the number of things. You just don't have something. And so eventually they came to the point where like we need to represent nothing. And so this is a representation of nothing, 0. So here's a little number line that kind of explains where those kind of numbers lie on the number line. Because they are all real numbers, they can be represented on the number line. Some of mine may not be exactly where they are. I just kind of guesstimated because honestly, it's not that big of a deal for me at this point in time in my life and with this class. Next bit is just going over inequalities. So we have our less than sign, our greater than or more than sign, our less than or equal to sign, which you could also say no more than, and our greater than or equal to sign, or no less than. So inequalities meaning it's not equal to something, but it's around there. Like I can have no more than 14 students in my classroom right now and still be okay with the whole 1 meter apart in my classroom to avoid my kids and me getting COVID. So when we have intervals, so just a brief overview of our intervals, we have the bounded intervals. So bounded, we don't have infinity in there. We have two numbers that we're in between. And we have open with our parentheses and closed represented with our square brackets. So our square brackets mean or equal to, we're including that number, and our parentheses, we're not including that number. So it's just a less than or a greater than. And so sometimes you can have one that you include and one that you don't. So that's when you'd switch up the brackets and the parentheses. When it's unbounded, then we have an infinity involved. So it can be 3 or greater. So we need to have at least 3 people come to this party, and we could have an infinite number if we really wanted to because we have a lot of space. You could also have negative infinity to positive infinity. So it goes all of the directions, every single number. So we would just say all real numbers. But typically when it's all real numbers, I use the all real number symbol instead of writing out all real numbers because I'm lazy and I don't have to. Absolute values are the distance from 0. So how far did I walk from 0 to get to this spot? So if it's negative, yes, you're walking backwards, but you're still walking a positive distance. Distance isn't negative. You don't drive backwards and suddenly your mileage starts going backwards. It starts decreasing. No, people would be doing that all the time to make their cars more valuable. That's not how it works. So anytime we have an absolute value, it is a positive number. So if we have a negative value, it's going to be equal to that positive situation. If we have two numbers multiplying together inside of an absolute value, you can separate them and put them into their own absolute values. Same thing when it comes to dividing. Just keep in mind that we can't divide by 0. And that's something we're allowed to do, that is undefined. When it comes to some of our vocab, my students should be doing a vocab list right now. So term is when we're talking about the parts of an algebraic expression. So 3 plus 4x. 3 and 4x are both terms. They're separated by the plus and minus signs. When it comes to coefficients, that's the number in front of each term. So again, if I have something like 3 plus 4x, I have two terms. And then my coefficients are the numbers in front. So here we have the 3, it is its own constant coefficient. And then here the 4 is a coefficient for the x, because it's a number in front of the x. There's a 4 for that term. When it comes to exponents, here are exponent rules. Again, these are things that my students should have learned in the past. We're just doing a very brief overview. So when it comes to exponents, when we're multiplying the same base, so we have a little multiplication sign here, multiplying the same base, we add those exponents. So that's like if you had x squared times x cubed. The squared means we have two x's multiplying. The x cubed means we have 3, so we have a total of 5 x's now. So 2 plus 3 would give you that 5. When it comes to division, we're subtracting. So say I have x squared on top, x cubed on bottom. That means I have 2 x's on top, 3 on bottom. So 2 of those will cancel out. I'm left with 1 on the bottom. How I like to do it is I like to do big minus small. So here the 3 is larger than the 2. So I'd do 3 minus 2, which would give me an exponent of 1. Because the 3 was larger, that means I have more things on the bottom. So my answer is going to be left on the bottom. The x to the first would be left on the bottom. When I have a negative exponent, I have this little bunk bed story. So everyone goes to some sort of camp where they've been in a bunk bed, and everyone has their preferred bunk. So I prefer the bottom bunk because I'm terrified of rolling and falling off the top bunk. I just don't want to do that. That sounds like a very terrible time for me. So I have negative feelings about being on the top bunk. And so I prefer to be on the bottom. When I'm on the bottom, I'm happy. I have positive feelings. So these exponents are kind of like the feelings of our base. So the A is our base in this case. Because he is technically on the top bunk, it's over 1, he has negative feelings about being on the top bunk. He's like me, doesn't want to roll off. So then we move that to the bottom, and we end up with 1 over A to a positive end. Now that he's on the bottom bunk, he feels a little bit better about himself. But basically it just means that you're flipping the fraction. And then because we have a 1 on top, that n could be on the outside. Doesn't necessarily have to be down with the a, 1 to the nth power is still going to give you 1. And then we have the little rule of a to the 0 power. Anything to the 0 power, although that is, as long as a is not equal to 0, is going to give you 1. And I like to show a little example of that. So if I start with 3 to the first power, that's just going to give us 3. 3 squared, in order to get from 3 to 3 squared, that means I'm multiplying 3 times 3, which gives me 9. 3 cubed, I'm multiplying by another 3, so that would give me 27. So as I'm going up the exponents, I keep multiplying by 3, which means if I'm going the opposite direction, I'm dividing by 3. So 27 divided by 3 would give you 9, which is the 3 squared. If I went 3 to the first, I divide 9 by 3 and get 3. So in order to get 3 to the 0 power, I do 3 divided by 3, which would give me 1. So again, this is why it kind of doesn't work for 0, because you would have to divide by 0, and we're not allowed to divide by 0. Next bit, if we have an exponent on the outside and things are multiplying inside, so there's definitely a multiplication symbol, not addition, not subtraction, we just distribute the exponent to both. So we have a to the power of m and b to the power of m. And if we have an exponent to an exponent, then we're multiplying those together. So if we had something like x to the third power squared, that technically means we have 2 x cubes. And I just shown before that we add those together, so 3 plus 3 would give us 6. Or we could just do 3 times the 2, which would also give us 6. And then these last bits, just like with the multiplying, if I'm dividing and I have an exponent on the outside, they go to both, so a to the m and b to the m. And if this is, notice this is squared, it's not a variable, but strictly squared. So if we have a squared under absolute values, it's going to be the same thing as if you had absolute values and then squared that a. Doing a couple examples, I have 2 bases that are the same here, my x's. So that means I'm going to add their exponents. I don't have another 2, so that 2 will stay the same. And 4 plus a 3 will give me x to the 7th power. Next one, and this is the last one I'm going to do on here. The others I'm going to save for my students. We're going to do those in class together. I have a 4 on the outside, so this is going to go to the x. But not only is it going to go to the x, this 2 is also in there. So anything that's multiplying inside there, they're all going to get the 4th power. So I have 2 to the 4th power and x to the 4th power. I also have this x to the 3rd power here on the outside. So 2 to the 4th power is going to give me 16. And now I have these 2 x's multiplying together, which means I will add those exponents for x to the 7th power. So scientific notation, again, my students should have seen this, especially in science class. This is something that is very common, against scientific notation. One of the rules is that our m has to be a 1-digit number, so only 1 digit before the decimal point, which means it can be 1 or it can be up to 10, but it has to be a 1 digit before the decimal, and then you can have quite a few decimals afterwards. And then our n is going to be an integer, meaning it could be positive, it could be negative, it can't be a fraction or a decimal. We need a positive or negative integer there. So this first one, we're going to write 970,000 in scientific notation. So I see at the very front, I have a 9 and a 7. Again, I want this to be smaller than 10, so 9.7 is smaller than 10, but larger than 1. And then that means I would have moved my decimal 1, 2, 3, 4, 5 places, which means I have x to the 5th power. So it's always the number of places you move. I like to see it as like the number of numbers that I have after my new decimal once I've moved it. It's a little bit easier for me to just count numbers than it is for me to do the bunny hops. The next one, we have a negative exponent here, which means we're making our number smaller than what it is. So remember, the negative means that we want a fraction, so technically we're dividing this by 10. Because we're dividing it by 10 so many times, it's going to be a very small decimal. So I'm starting with my 8.3, so I'll start 8 and 3. And technically I will have moved my decimal 4 times. Because I'm wanting this to be smaller, I'm moving it 4 times. 1, 2, 3, 4 to the left to make it a smaller number. I also just like to put 1, 2, 3, 4 zeros, and then that decimal is going to go in between. So we had started at the 8. Before the 8, we moved 1, 2, 3, 4 spaces. That's just my little trick for it. So I just put however many zeros in front of the first number and then put the decimal in between the first and second. And then here, it's a little bit more complicated. So order of operations tells us that we need to work with exponents before we do anything else. We can't really do the 3 times the 10 to the second power right now. It's going to be a little bit more work than what is necessary. So I'm going to do my exponents here first. So the 3 goes to both the 3 and the 10 squared. So 3 cubed is going to give us 27. Then we'll have times 10, and then 2 times the 3 there will give us an exponent of 6. And we still have our 2.4 and 10 to the negative 5th. And then the next thing I want to do is I don't like that this number 27 is larger than 10. So I know that I'm going to want my decimal point to move between the 2 and the 7. Because I'm making this a smaller number, that means this 10 would make it bigger. So I'm adding a 1 here. So I've got 2.7 times 10 to the 7th power now, and 2.4 times 10 to the negative 5th. So when we're doing this, we're kind of multiplying like terms, and it's not necessarily like terms, but like bases. So our numbers that don't have any variable or any exponents are going to be multiplied together. And then our tens are like common bases. So they're like x to the 7th and x to the negative 5th. So those, because they're multiplying together, everything is multiplying together, so we don't have to worry about distribution. We're going to be adding those together. So this will be 10 squared. 7 plus a negative 5 will give us that 2. And then we're multiplying the 2.4 and the 2.7, and we end up with 6.48. You could also just like make everything its own number and multiply it all together and then kind of do this afterwards. I just think it's been more work than I really want to do. Probably this is more fun, to be honest, in my opinion. I'm a little weird though. Let's keep it clear. All right, our next bit, we are doing properties of radicals. Again, these are things that my students should be somewhat familiar with. So when I have any kind of root and an exponent on the inside, that exponent doesn't necessarily need to be in the inside. It could move its way to the outside. If I have 2 things that are multiplying underneath the same radical, then they can be together under that same radical. So you can separate them, you can pull them apart. These actually all work either direction. And then if you have, oh, that's the wrong color. If you have 2 variables that are dividing and they have the same radical, you can put them underneath the same radical. Again, anytime you have anything that's dividing, you want to make sure that the variable is not equal to 0. And then here we can, if we have a radical within a radical, that seems really disgusting and kind of not necessary. So if we have a radical under a radical, we can just multiply those indexes together. So these numbers here inside the check are called the index. So we would multiply those indexes together. And then anytime we have the same radical with the same exponent, or that index and exponent are the same, they end up canceling each other out. So the inverse of a square is a square root and vice versa. And we do have to be careful if we're canceling things out. Then if the exponent and index are even, we need to make sure that we have that square root, because we can have the n on the outside. If we had the square root of -4 all squared, we still have that instance where we're taking the square root of a negative. So we have to be careful with that. So we want to make sure we have absolute values. If they're odd with cubes, it doesn't really matter, because the cubed root of -27 is -3. The cubed root of +27 is +3. It really doesn't matter. So then here we're going to do a few examples. Whenever I look at this, the first thing I notice is the cubed root and the 125, because I know the cubed root of 125. So I'm going to kind of put this in parentheses and have the 2 on the outside. And so the cubed root of 125 is 5. And I'm squaring that with that 2 that I set to the side. And 5 squared gives me 25. The next bit, I have the same index here. So because these are under the same type of radical, I can put them under one radical. So this is all cubed root. X squared in one, x in the other. And I know x squared times x is going to give me x cubed. And then the cubed root of x cubed, these are both odds. They cancel each other out, and we don't have to worry about absolute value mess. All right, so when we're simplifying radicals, so we have an expression they want us to simplify. We know that it's in simplest form when there's nothing under the radicand, so that the radicand is the actual radical symbol. So no, the radicand, sorry, is what's underneath, so radicand. The radical is a radical symbol. The radicand is what's underneath. So underneath the radical, there's nothing that we can take out that we actually know the square root or cubed root or fourth root of. We're breaking it down. There's no nth root in the denominator, so we've gotten any kind of radical out of the denominator. Any radicals in the denominator, in the bottom of the fraction, it makes it irrational. So we want those just to stay on the top, just in the numerator. And no two terms have the same radicand and index, meaning we don't have any terms. We don't have any terms that are square root of 7 and square root of 7. So x square root 7 plus x square root 7. Those we would be able to combine. Those are called like radicals. So if they have the same index and the same radicand, they can be combined the same way that you would do like 3x plus 7x. We don't know what the square root of 7 is off the top of our heads. It's a really gross decimal, so we can treat it like a variable. So we can say 3 square root 7 plus 7 square root 7. We can combine those, so 3 plus 7 will give us 10 square root 7. One of these examples. So I have a cubed root, so I'm looking at these, and one of the things I want to do is figure out if there's anything inside or underneath that I know the cubed root of. So in 81, I know that I could take out a 27. I know the cubed root of 27. So if you're not really familiar with your perfect squares or your perfect cubes, that's something that you're going to want to kind of have written out somewhere. And so if I took out a 27 from 81, I would have a 3 left. So technically, underneath my radical, instead of 81, I have a 27 times 3. That's the same thing as 81. And because these are multiplying, I can separate them. And the cubed root of 27 is just 3. So I have 3 cubed root 3 here, 2 cubed root 9. I can't combine the cubed root 9 and the cubed root 3. They're not the same underneath, so I'm going to leave that. And then I have this fraction. In my classroom, fraction is an F word. It is the F word instead of like the F word, saying that, like you say, what the fraction? And so I don't want the radical on the bottom, technically, because we have that fraction. This is like cubed root of 1 over cubed root 3. Of course, cubed root of 1 is also just 1, so I can just say 1 over cubed root 3. But I don't want it to be cubed root 3, so I want to multiply it by something that's going to turn it into a cube that I know. Because it's 3, I could multiply a little bit more and make it into 27, because I know the cubed root of 27, I just did it. In order to do that, though, in order to turn 3 into 27, I'd have to multiply it by a 9. Because it's under a cubed root, the only thing I can multiply a cubed root by is another cubed root. And what I do at the top, I also have to do at the bottom. So then multiplying across the top, we've got cubed root of 9. And multiplying across the bottom, 3 times 9 would give me cubed root of 27, which is just 3. So then minus 2, and then that became cubed root of 9 over 3. Now what I see here is I have two things that have a cubed root 9 in them. So I have one over here has a cubed root 9, one over here has a cubed root 9, which means I can combine these. I can see it as like 2x minus 2/3 x. So I'm going to be combining the 2 and the minus 2/3. That's a fraction and a whole number, so I wanted a fraction minus a fraction. So that would be, what, 6 over 3 minus 2 over 3. There's still cubed root 9 there. And the 6 minus the 2 would give us 4. So we have 4 over 3 times cubed root 9 minus 3, cubed root of 3. And we have, again, a cubed root of 9 and a cubed root of 3. Those aren't like radicals because they don't have the same number underneath. So this is as far as I can go. Next one is a little bit different. We're multiplying some things in. So when we're multiplying, I'm looking at my negative 4 times the 3. So the numbers on the outside multiply together. We would get negative 12. And then the square root 6 and the square root 2, they're both under a square root, so they can multiply together, which would give me square root 12. Distributing in negative 4 and negative 5 would give me positive 20. And square root 6 times square root 3 would give me square root 18. And then we still have that plus 5 square root 48. And so from here, I have a few numbers now that I need to break down. I'm going to break down my 12 first. So this is a square root, so I'm going to take out of 12 something that I know the square root of. So I know 2 and 6 can make 12, but none of those have a square root. I can also do 4 and 3, and I do know the square root of 4. So I'm going to take out a 4. We're left with a 3, which means we have square root of 4 times 3, which is 2 square root 3. So now I have that negative 12 from the start, and it's multiplying with the square root 12, so it's going to multiply with the 2 square root 3. Next thing I want to do is break up my 18. Off the top of my head, I have 3 and 6. Don't know the square root of those. I also have 2 and 9. I know the square root of 9. And so 9 times the 2, square root of 9 is 3, so I have 3 square root 2, simplified. I have the 20 that it started out with, and that will be multiplying with the reduced version. And then the last one I want to look at is 48. And sometimes you can pull out multiple things if you don't see the largest square root right away. So the largest square root that we can take out of 48 is 16. But say you didn't see that right away, say you just saw 4, you're left with 12. You can take out another 4, you're left with 3. And then you see, oh, I have 2 4s. So if I have 2 4s underneath the square root, that's going to be taken to the outside. Square root 3. So if you had seen the 16 to begin with, 16 and 3 give you 48. The square root of 16 gives you 4. And again, this will multiply by the 4, or the 5, sorry, that was there to begin with. So simplifying all these numbers on the outside. And then I do have 2 numbers that have the same radicand. So that's square root 3, same radicand, same index. So those can be combined. And the negative 24 plus a 20 will give me negative 4 square root 3. And there's nothing to combine with the 60 square root 2, so that will stay the same. All right, so our next bit, I said before that we don't like having radicals in the denominator. Say that we had something that was a little bit more than just like a square root 3 or a cubed root 7 or something like that. Say it was a binomial. If we have a binomial and a radical in the denominator, we want to use this thing called a conjugate. And so conjugate basically just means that we have different signs in between. So that's the only thing that we're changing, and it can go either way. So if we start off with a plus, we would change to a minus. When we do that, if we multiply by a conjugate, the middle term disappears. So it's like x plus 2 times x minus 2. Whenever we do the distribution and multiply everything in, we have x squared minus 2x, and then plus 2x minus 4. So that middle term there cancels out. And so our goal here is, because the middle term cancels out, that means it's going to end up canceling out our square roots. We're going to be multiplying the square by itself, or the square root by itself, making it a square, making it cancel out. And so our goal is to do that, just cancel out any radicals that we have in between. So when we're simplifying or rationalizing either a numerator or a denominator, there are some cases where you can be asked to rationalize a numerator. We're going to multiply whatever it is we're rationalizing by the conjugate of that thing we want rationalized. So most of the time, you're going to be rationalizing the denominator. So you're going to multiply both top and bottom by the conjugate of the denominator. And then we simplify as much as we can. And we're good when there's no more radicals in our denominator. Of course, again, you could be asked for numerator, and then in that case, you just don't want radicals in the numerator. I'm going to start off a little simple. So the first thing I want to do is find my conjugate. So I'm rationalizing the denominator. So I just want to multiply it by the opposite of the inside there. So square root of 5 plus 1. That'll be over, again, the same exact thing. So basically we're multiplying by a version of 1. Something divided by itself is just 1. So because we're multiplying by 1, we're technically not changing it. I like to call it putting makeup on a pig, especially since it kind of looks gross. So I'm going to multiply across the top, so the 1 will distribute in to just give us square root 5 plus 1. And most of the time, after my students get a little bit more involved with this, they don't necessarily have to take the time to multiply out the denominator. I'm going to do that just for this case. So we would have, do you think I'm going to change the color of this? We would have square root of 5 minus 1 times its conjugate, so square root of 5 plus 1. I'm going to do a bit of distribution. So square root of 5 times square root of 5 is square root of 25. Square root of 25 is just 5. And then we have square root of 5 times 1, which is just square root of 5. Negative 1 times square root of 5 is negative square root of 5. And negative 1 times positive 1 is just negative 1. So then here my radicals cancel out. The plus square root of 5 minus square root of 5. I'm left with 5 minus 1, which is 4. So then I'm going to put that back into the denominator. It's just 4. And now I don't have anything left to simplify. I have a square root of 5 plus 1, which I can't add, and I can't reduce square root of 5 over 4 or 1 over 4. So this is all we got to do. The next one I'm going to save for my students, but this is pretty much the gist. You just distribute the stuff on top, and the bottom, it should all cancel out because of that beautiful conjugate. Here, it's a little bit different. They want us to rationalize the numerator. Because we're rationalizing the numerator, I want the conjugate of the numerator. So we're just changing that one sign. And again, we always multiply top and bottom. So it looks like the top part is going to be a bit more complicated. So I'm going to multiply the denominator first. Get the easier part out of the way, in my opinion. So I'm going to do 6 square root 3, 6 square root 5. And then we're going to take the top and kind of just move it over to the side. We're going to do it all over here. So square root 3 times square root 3 will give you square root of 9. Square root of 9 is just 3. Square root of 3 times square root of 5. We can multiply those together because they're both under square root, so it'll be square root 15. And then we'd have minus square root 15. And then negative 5, negative square root 5 times positive square root 5 will give us negative square root 25. Square root of 25 is just 5. So again, our middle terms cancel out. We have no more radicals. 3 minus the 5 gives us negative 2. So we have negative 2 on top. And here I notice that all of my numbers on the outside of the radicals, so I have a 6, and a 2, they could all be reduced. So I could, I guess, undistribute the 6 there, if that makes more sense to you. So 6 square root 3 plus square root 5. And if this is over negative 2, this will reduce here to just negative 1 over 3 square root 3 plus square root 5. You do want to make sure that's reduced as much as possible. All right, next bit. If, say, something is in exponent form and we see that the exponent has a fraction, then we can change that into the radical. So if you think about it, if we have a squared and you're taking the square root, The reason why this works is because the square root is just dividing the exponent by 2. And the 2 divided by 2 gives you an a to the first. So this works the same way. Whatever it is that is on the bottom of the fraction, so the denominator, is going to be the index of your radical. We have an n on the bottom here, so we end up with a root n. We have an m on top, so that means we have an exponent kind of out on the outside, or it could be again on the inside. So kind of two ways to look at it. And then our index is the bottom of the fraction, the denominator. So over here, we want to change from radical, so we see the square root, so this is in radical form, into exponential form. And so this 4, it is a little bit of a confusing, I probably should have put a bit more space in. That's a 4th root, not an x to the 4th power, that's the 4th root. So I have a 2x in front, I'm going to leave that for a second, and I'm just going to deal with the radical and make it into an exponent. So this is an x to the 1st power. And then I have my index, which I know is going to be at the bottom of the fraction. And the exponent is going to be at the top. And then that's our other x. And now I have two x's that are multiplying. So we have our exponent rules. Anytime we have our variables or our bases multiplying, we're going to add those exponents. So 1 3/4. I don't like to keep it as 1 3/4. I like to make it into an improper fraction. So 1 plus 3/4, that's the same as 4 over 4 plus 3 over 4. And then now that I have the same denominator, the 4 and the 3 would give me 7. So I have 2 x to the 7 over 4. And that's it. Now I have just exponents. I don't have any more radicals. And it's just one exponent, so we're good. Next bit, I want to simplify this a little bit. I do have an improper fraction. So technically, it's not simplified. So our last answer wasn't technically simplified. The more simplified version was putting it into the radical form. So often I will turn this into the radical form just to make it make a little bit more sense to me. This negative here means that it's not happy where he's at, so he's going to go to the bottom bunk. I like to get rid of my negatives first. So the entire 8 to the 5/3 is going to go to the bottom. I don't like that we have the 5/3, so I'm going to change this up a little bit. It'll be 1, and I'm going to change this because I have a 3 on the bottom. That means I have a cubed root of 8 to the 5th power. And actually, I know the cubed root of 8. And I said before that we can just kind of rearrange this a little bit. So I have the cubed root of 8, and I know the cubed root of 8 is 2. So I can say that's 2. And then I still have that 5 from before. So 2 to the 5th power is going to give me 32. So it's really just 1 over 32. I feel like that looks a little bit better than to a negative fractional exponent. Our next bit looks a little complicated. Tell you right now, it's not that bad. We're going to combine our numbers with numbers, or x's with x's, or y's with y's. So I'm going to first start with the easiest, the numbers. 4 times the -3. Again, nothing's adding, so we don't have to worry about the whole distribution process. We just combine our coefficients and our variables. 4 times the -3 is going to give me -12. And then I have my x's. Because these things are multiplying, that means I'm adding my exponents. So 2 plus -1/3. That's 6 over 3 minus 1/3, which makes it 5 over 3. So x to the 5/3. And then my y values, or my y variables. I have 3/2 plus -3/5, so -3/5. Those aren't the same denominator, so I want to make them the same. That means I need 10, so that would be times 5, 15 over 10, and then times 2 would be 6 over 10. 15 minus 6 is going to give me 9. So this is y 9/10. And I can't break this down any further because they aren't actual numbers. So when you have variables, we can just leave them in this fractional form. If we have numbers, we want to see if there's anything that we know the square root, cube root, fourth root, any of those. And this last bit, again, I'm going to save for my students. And so I hope you guys have gotten something out of this. If you have questions, feel free to leave a comment and I can help you out there. If my students have the most common questions, I am going to be making a video out of that as they're doing their practice. So if you feel like this could help someone out, please share it, like and subscribe for more videos, and I will check you later. Be sure to be kind to one another.